My name is Satish. I'm from Intel Corporation. This is joint work of Intel Vectorizer team along with Florian Hahn from ARM. So I'll be giving a status update on outer loop vectorization in LLVM, where we stand currently and our future plans. Let's begin with some background information. So as we just saw in the previous talk, LV does not support outer loop vectorization. A project which outlined outer loop vectorization support was actually presented at the 2016 LLVM developers meeting. Since then, VPlan, which is basically a new vectorization infrastructure, was added to LV in early 2017. So VPlan, what it allows us to do is it allows us to explicitly model and evaluate different vectorization scenarios. And we can actually do this without modifying the underlying IR. So if we decide not to vectorize the loop, this has the advantage of preserving all the existing LLVM analysis information. So once we evaluate different scenarios, what we can do is we can select the scenario with the best cost, and if the decision is to go with vectorization, we can actually materialize the same, which basically means generating vector code. So I've shown an example of a loop nest here. So given this loop nest, we have several possible choices for vectorization. So we have listed some here. So VPlan, what it allows you to do is you can actually evaluate these different scenarios and pick the best one. And if it happens to be vectorized, if the decision is to go with vectorization, we will go ahead and vectorize basically. So let's actually start out with some terminology. We are going to use a within this presentation, we are going to use the terms uniform versus divergent a lot. So we thought it's actually a good idea to make it clear what we mean. So we actually say an inner loop is uniform if all the vector lanes are going to execute the same loop iterations. And we are adding something called trivially uniform, which basically means that the loop bounds are loop nest invariant. Similarly, a conditional branch is said to be uniform if all vector lanes are going to take the same branch target. It is divergent otherwise. So similarly, we have the counterpart trivially uniform. Basically, the branch condition, we can prove it's loop nest invariant. So the basic idea is trivial versus non-trivial, we don't need divergence analysis. So in order to do more sophisticated uniformity, we will need divergence analysis that Simone Moll just talked about. So, following this, we actually presented a 5-patch series, which was the aim of this patch series was to add outer loop vectorization support in LV. So this was done at the 2018 Euro LLVM developers meeting. So the goal here was to introduce support for explicit outer loop vectorization in LV. We actually began with really simple loops. So we started out with outer loops where all control flow within the outer loop is trivially uniform. So we started out with inner loops which are trivially uniform. And even there, we kind of divided the problem into 3 subsets actually. So the first patch series, the goal was to handle all control flow within outer loops where everything is trivially uniform, and slowly start adding more and more features basically. So patch series 2, it starts adding support for control flow where the inner loops still remain trivially uniform, but other branches can be divergent basically, trivially divergent. So, and patch series 3 is where we start analyzing uniform versus divergent control flow using some kind of divergence analysis. So this is where we have plans to use the divergence analysis from RV. And the next step would be supporting divergent inner loops. So we go from trivially uniform inner loops to divergent inner loops. So the idea here is to transform. So we are basically building upon what we have already added. So we will be transforming the inner loops to be uniform. So, and then support multi-exit inner loops, basically. So again, the idea is use what we have already implemented, and so transform the multi-exit inner loops to single-exit inner loops. So where are we currently? So currently what we have done is like, in order to do all this implementation, we wanted to keep the inner loop vectorization path stable. So basically, our main goal has been to keep the changes, our changes as a NFC as much as possible for the inner loop vectorization path. So all the outer loop vectorization support is added in an alternative vectorization path. We are calling it the VPlan-native path. So all outer loop vectorization support has been added in this new path. So, and it's under a feature flag which is actually off by default. So currently, patch series 1 implementation has been completed and it has been committed to LLVM. So if you actually go now and try it out like VPlan-native path, you will see the loop example which is shown there getting successfully vectorized actually. So like I said, like we are only doing explicit outer loop vectorization. The pragma highlighted in red is the way the user currently tells LB to do outer loop vectorization. If you see, we are still using pragma clang loop vectorize. The eventual goal here is to go to pragma OMP SIMD, but as pointed out, like OpenMP support is not yet there in Clang. So if you are interested, actually there's a talk later like where we are talking about adding OpenMP semantics to Clang. So, and folks who are familiar with LV know that LV does not preserve uniform control flow. For the most part, like it tries to generate vector code in a single basic block. There are some exceptions, but that's typically the norm. This is what the vector loop looks like right now. So you can see that we are preserving the control flow within the scalar loop. The CFGs for the scalar and vector loops look identical, basically. So the key takeaway here is vector code generation has been enhanced to preserve uniform control flow now. Other takeaways. Right now, we are actually focusing on functionality versus performance. So right now, you will see that the VPlan-native path assumes all loads and stores to be non-unit sided. So you will see gathers and scatters being generated. So that's an example out there. And similarly, like VPlan-native path does not run any cost modeling or any kind of uniformity or scalarization analysis yet. So all instructions are simply widened. So you can actually see that in the branch backage condition. So the compare is simply widened, and we are extracting the value for lane 0 and using that as the for the conditional branch, basically. And like I said, so outer loop vectorization is only targeting explicitly marked loops, so we are not doing any kind of legality checks. So once the user tells us that it's okay to vectorize the loop, we go ahead and do that. So we are currently working on our patch series number 2. So this is where we start handling trivially divergent branches. So you can see the example there again. So the inner loop, as you can see, the bonds are loop invariant, but the if check is not. So in order to generate proper code for this, we will need predication and mask vector code generation support. So this is what we are planning to add as part of patch series 2 in the VPlan-native path. So patch series number 2, we actually have 3 patches planned. So the first patch in this series implements the needed predication and control flow linearization support. The basic idea here is to generate VP instructions which will compute the basic block predicates. And these are the values which will get used to mask instructions as needed, basically. And it will also linearize the control flow. The second patch in this series actually adds a specialization of VP instruction, VP for 5 nodes, so VP 5 node. We plan to use this for properly blending fees into selects, actually. And finally, we will need changes for mask code generation support in VPlan-native path. That will come as patch 3 in this series. The first 2 patches are already out for review, basically. And just an example of what the VPlan CFG looks before and after predication. So if you see on the left-hand side, the block marked for body 3 has 2 successors, the then successor and the L successor. On the right-hand side, you see that the control flow has been linearized. So for body 3 has only 1 successor. It goes into the then block and then the else block. And you will also see that we have computed a block predicate for the then block, which is basically the value from the compare. And the else block, again, we compute the block predicate, so which is the not of the compare value. So VP62648 out there is what is used to mask the instructions as needed, basically. So at this point, Florian will take over and talk about VPlan-to-VPlan transformations.
Okay, so in this section, I want to briefly talk about how we plan to model different vectorization scenarios and how to explore them in VPlan. The basic idea here is that we first transform the IR loop and IR loop nest into a VPlan loop, which is a hierarchical representation of a loop nest, and use that as a starting point for a transformation or planning phase where we have a set of transformations that enable vectorization. So here we have some transformations that take VPlans as input and produce a new VPlan that represents a certain strategy. So for example, we have the predication that Satish talked about earlier, or SLP, for example. And then, so this will generate a set of VPlans reflecting different strategies. And then from these VPlans, we can apply further transformations, like we can either apply out-of-loop vectorization to them or in-loop vectorization to them. And in the end, we end up with a set of VPlans that reflect the different choices we could make. And then the next step is to evaluate the cost of each of those VPlans and pick the best one. And then once we have decided which one we choose, we basically materialize the VPlan and generate vectorized IR. So this structure has some benefits over the way things are currently done in the Loop Vectorizer. First of all, it allows for a better structuring of the different components, which is a drawback of the current Loop Vectorizer, where everything is quite entangled. So with this VPlan-to-VPlan transformation model, the idea is to have a set of separate transformations for specific strategies. And those transformations, like predication or SLP, they are responsible for just the legality checks required for this kind of transformation, and then also applying the transformation by generating a VPlan that reflects the decisions. This also allows us to have the cost modeling separately from those transformations. And the cost model is basically just an evaluation of a VPlan. And with that, we can also, the transformations themselves can be developed independently with this structure from other transformations, from cost modeling, from IR code generation. And this allows us to incrementally improve this and bring up this whole infrastructure. And it allows working on different kind of VPlan-to-VPlan transformations, even though, for example, cost modeling based on VPlan is not implemented yet. And another advantage of this approach is that those passes, those transformations basically can be tested much better independently, whereas because the structure allows that. Of course, with this approach, there are some practical issues that we have to consider while we work on this infrastructure, bringing it up. The first of all is creating new VPlans is not free. The VPlans might represent a loop nest with multiple loops, and so we need ways to represent changes to them efficiently, because some transformations like SLP or predication, they might only apply to a single loop or basic blocks, and we plan to introduce the notion of VPlan diffs to represent local changes to certain parts of VPlans. Another thing with this structure is where we have different transformations that can be applied. We have to make sure that we do not create too many VPlans, so we plan to use heuristics while we go along and apply those transformations to avoid exploring VPlans, too many VPlans that might turn unprofitable. And because we use this VPlan representation, there's one problem that it's harder to reuse IR-based analysis. But we started work already to make sure that we can use like dominator analysis, loop info based on VPlan. And so to end this section, I want to briefly give a quick example of how we can use this model to improve the way interleaved memory accesses are handled in LLVM's Vectorizer. So consider this simple loop on the slide, which basically just adds 1 to all the even elements and 2 to all the odd elements in the array. There are multiple ways we can deal with those kinds of interleaved memory accesses. One is we can do what the current Loop Vectorizer does, is basically interleave the memory accesses and then extract the even and odd elements in separate vectors, and then go on and widen the both add operations, and in the end create a shuffle and store the result, which is fine on some architectures where extracts and shuffles are cheap. For example, on AH64, there are instructions you can use to do that kind of thing. But it is expensive for other targets. So for example, x86, the loop won't vectorize as it is currently. And another thing we could do is use some kind of loop-aware SLP, where we apply SLP to the loop body and then widen the result. So we could combine the loads, combine the add instructions to operate on the same vector, and then create the store as usual. And this results in simpler code and is more efficient on targets without cheap extracts. So we're running out of time. So just quickly, this is just an example where that can be modeled using different VPlan-to-VPlan transformations, and the work has already started. There is a patch up for review to add this SLP capabilities on top of VPlan. And to wrap up, just a few closing thoughts. As there are now 2 code paths for vectorization in the Loop Vectorizer, our goal is to converge both vectorization paths as soon as possible. And of course, we continue working on the proposed patch series that was mentioned earlier. We're also working on adding inner loop vectorization, legality, and cost modeling into the VPlan-native path. And we created a ticket to track all the VPlan-related tasks if you're interested. And the end goal is for the VPlan-native path to become the default once it's a superset of the current Loop Vectorizer. And so in summary, LLVM's Loop Vectorizer can now vectorize simple outer loops in the VPlan-native path. VPlan-to-VPlan transformations for stuff like SLP-aware loop vectorization and predication seems a good way to model those things. And code generation and cost modeling, as mentioned earlier, is not implemented in VPlan yet, or the code generation side is not as efficient as it could be. So it would be good to get some help from the community to work on that. And there are also 2 related talks later on. One is about the vec clone path for function vectorization via the Loop Vectorizer you might be interested in, and methods for maintaining OpenMP semantics, which is what Satish mentioned earlier. Okay, so that brings me to the end of our talk, and we now open for questions.
Thank you, Florian and Satish.
So the current cost model in the Loop Vectorizer is fairly local, meaning that it checks one instruction at a time. What is the plan for, like, is there a plan to have a cost model that checks the entire vector plan? Or like, what is the intention, or how do you envision the new cost model?
So, as you mentioned, like, it is, for example, it will definitely need changes for outer loop vectorization. So the current cost modeling, if you're aware, like, it computes per iteration cost. So it doesn't account for like inner loop iterations and so on. So we haven't thought too much about it, but we know that it will definitely need a lot of work. Go ahead.
This is Hideki from Intel. Let me add to that answer. So there is actually a discussion regarding the vector idiom and stuff that is currently recognized at the target level. So I'm actually working with the target guys to decide what kind of common interface that we could use to make sure that what vectorizer should know as an idiomatic operations to account for proper cost modeling of that idiomatic operation versus what CoreGen will actually handle, to make sure that it's actually one-to-one most of the time. So there is a discussion in the talks to make that happen. It hasn't materialized yet.
Thanks for the talk. So I got two questions. So first question is, so what do the VPlan diffs look like? And wouldn't that complicate cost modeling and other transformations?
So I think the idea here is to use them for local changes. So say for SLP, you replace some instructions with some other VPlan instructions. And then the plan is to have an interface where you have the original VPlan, you apply the diff when you iterate over the original VPlan, and then you when you iterate over the diff and the original VPlan, you just see the result of the diff applied, basically.
Okay. But that would be local, right?
Yeah, I mean, that's not for all the transformations you can make for predication. It probably wouldn't make sense. But for stuff like SLP, it would make sense.
Okay. So second question, if I may. How are you planning to handle divergent loops, and how are you planning to represent the transformed uniform loops in VPlan?
So the transformation will be like a VPlan-to-VPlan transformation. So we will kind of change the control flow within the VPlan CFG, basically. So.
Okay, so we're planning to add new instructions, for example, or like gamma nodes, stuff like that.
Yeah.
Okay. This is one advantage of the
VPlan. So we don't touch the underlying IR.
And we have the flexibility to add stuff that allows for easy representation of concepts.
Right, but you still have to transform your own IR, right?
Yeah, in the end.
Right.
But that's just after. It's completely separate from the transformations.
Thanks.
We have time for questions.
So with outer loop vectorization, will you do reordering transformations like interchange or unroll and jam? And the second part of that is, what do you do about dependence information?
So if we do any interchange or unroll, we are at least for now, we are expecting it to happen before we hit Vectorizer. And as far as legality checks are concerned, so our initial goal is to get support for OpenMP 4.5. So it is supposed to be explicit, but we do have future plans to work on extending the legality checks for outer loop vectorization.
Yeah, but this probably needs general improvements to the way we do dependence analysis on multi-dimensional arrays, which is not the best in LLVM at the moment.
So then let's thank the speakers again.
Thank you.